Okay. I wanted to do a separate video for this. One, because the other video is getting very, very long. Now, there might be a third or a fourth video added to chapter 4 before we get done with it because it's a big chapter, right? It's you know, it's a big task to go through. I'll be gone next week, so I'm trying to give us a little bit of stuff to do throughout also. And I don't want to kill you with this. I want you to take your time to learn it. Okay, memorization doesn't do much. Uh, you learn it. Uh, it should be a natural, logical thing. Okay, so what we're going to do is we're going to look at Demorgan's theorem, which is section 4.3 in your book. DeMorgan's theorem is really special to me in the fact that it was the first pain uh, in the rear that I got through. That whenever I did finish it, I realized that I could do this. I can do this for a living. Okay, and so it's not it's not the most complicated thing, but it's also the way that they express it in the book is a little weird, and it doesn't have to. So hopefully through this video we can see it for what it is because it's super powerful. Now it sounds dumb. So the complement of a product of variables is equal to the sum of the complements of the variable. The complement of a product is equal to the sum of the complement. Okay. Or the complement of a sum of variables is equal to the product of the complements of the variable. Now you'll sit there and those are both sides of the same coin. Okay, the way they put it, we'll write it out. We'll write out one of them. Okay, uh, the complement of a product of variables is equal to sum of the complement of the variable. And also the complement of the sum of variables is equal to the product of the complement of the variable. Okay, they're the flip side of the same. All right, now that's a big wordy phrase for saying that uh all right, so the complement of a product of variables. Okay, so a product of variables, a product is a multiplication. And in the previous video I told you be aware that and gates and multiplication are going to become synonymous with each other. Okay, so just like with OR gates or addition. Okay, like we'll get there, but just know that it's coming. All right, so what this is saying is a complement of a product of variables. All right, a product of variables is a multiplication of variables or an anding of variables. Now the complement is the inverse. Okay, so it's saying if I have A ANDed with B and I have that knotted, it's equal to the sum of the complements of the variable. All right, so sums is an addition, like an OR gate, but it says equal to the sums of the complements of the variable. So now you're just going to have to look at this for a minute, okay? The complement of the sum or of the product of variables is equal to the sum of the complements of the variable. So the sum of the complement of the variable. Those two things are equal, okay? The complement of the product of variables, complement of the and is equal to the sum to the or of the complements of the variable. Our product of variables is one thing, ANDed it, and then we took a complement. The next thing is the sum, the addition of the complement. All right, so that's multiple complements, right? We're adding together multiple complements. Those two things are equal. Now, the same can be said about the complement of the sum of variables is equal to the product of the complement of the variable. So look at what we're able to do. All right, so these two things are equal, and these two things are equal. Okay. Now with an inverter, we can start messing around with logic using other gates. Okay. So let's say that we didn't have an AND gate, but we do have some OR gates and some not. Well, what can we do? We can use Demorgan's theorem to recognize that we can take an OR gate and some knots and make the same stuff. Okay, so that brings us to a new little thing. I told you that you could build anything with ands, ors, and not. And that's true. Those are the basic building blocks of our logic. But really, if you've got a not, you can build anything with not and. Or you could build anything with not or inverters and or. Okay? Because if I need an AND gate and I don't have an AND gate, I can use an OR and a NOT to get there, can I? Alright. So what we're looking at now, let's look at how we're going to express this without drawing it out all the time. So if you've got an AND, it's a multiplication. We put them right by each other like we would when we multiply. All right, so if we complement the output of an AND gate, we have an unbroken line over all of the product or all of the pieces of that product. Okay, so this is an AND gate with an inverter on the output of it. Okay, if we've got an OR gate with the inputs inverted, that means that they're going to be broken up like that. Okay, so the inputs are broken up. We don't have a solid line over that. Now, when we're looking at an OR gate, with the output complemented, then we do have X or Y and then a big line across there because it's complementing the whole summation of that. It's complementing the whole act of that, and rightfully so. When that becomes the complement of the input through an AND gate, right? Then we've got X and Y, but each one of those has their own little inverter to it, right? So those little dashes are telling you how many inverters we have, right? Right here we got two inverters, and right here we got two inverters. Right here we've got one inverter. Right here we got one inverter. Okay. So that means, let's say that we don't have, all right, we're saying we've got an AND gate with an inverter is the same thing as OR gate with inputs inverted. All right, so that's the phrase I want you to recognize. That a gate with the output inverted is the same as the opposite gate with the inputs inverted. Okay? Why is this important? All right, if we had all of our gates, we could look here and say that this is a cheaper thing to do. It's going to have the same output as this one, but we're only using two gates. We're using an AND gate and a NOT instead of three gates, an OR gate and two NOT, right? So if we come up with here, we can simplify it by using Demorgan's theorem and get it down to a smaller circuit, okay? We'll prove this in deeds in a minute, all right? So that's one thing. I already hinted at that, we needed a NOT and an OR to, make everything. Well, if we don't have an OR gate, right, we don't have this one. How would we make an OR gate if we didn't have an OR gate? Right? Yeah. Um, so if we put this inverter right here, that would be equal to that OR gate having inverters right there, right? And we already learned that if we put an inverter on the beginning, if we put two inverters over, in series with one another, like if this is a 0, that becomes a 1, that becomes a 0, like we invert an inverter, right? So right there, all right, so if we went and put an inverter on these ends, we've got our OR gate, don't we? Let's prove this. 0, 0, 1, 1. That's a 1, that's a 0. Now, let's look at either one of these being 1. That makes this a 0, that makes this a 0, that makes that a 1. So if any of these right here are 1, we're going to get a 1 out of here, just like an OR gate would. Okay? So we made an OR gate using Demorgan's theorem and adding extra AND gate to, compensate for the fact that it had already inverted at 1. Okay? Oh, man. Getting tired, y'all. Like my 7th video today. Alright. Now, we learned a little bit about things called NAND gate and NORs. Okay, AND is like an opposite of an AND gate, and a NOR is like the opposite of an OR gate. A NAND, all right, so I'm going to teach you one, and know that the truth of that one translates to the other. Okay, if you look at like GPUs and stuff or solid state drives, they'll show like fast NAND technology. All right, um, we use NANDs a whole lot. Reason being is because a NAND gate automatically has an and an inverter. Okay, if we have an and an inverter, we have everything that we could need. So instead of making a chip that has maybe 500 knots, 500 AND gates, and 500 OR gates, cool, we could get really good at making NANDs. And if we did 1500 NAND gates, we could make any of these components that we want. And I'll show you how. Now you're like, well, I've got the same number of components. Yeah, but what if you needed 600 AND gates and you only needed 100 knots, right? Or you needed no ores, you needed 1500 knots and 500 that's not going to add up, right? What if you needed 1500 knots? If you did it this way, you would have wasted 2/3 of your chip, because first of all, you wouldn't have enough because it was 500 to start with, but also, like, you know, you can get really good at making one thing and shrink the size down. So in the space that we had all these different components on there, some of them that we might not use, we might need more of one thing. We can make a substrate with nothing but NAND gates and then reconfigure how they do in the software, or the firmware. And so when I say that you need ANDs, ORs, and NOTs to make any circuit, you can make an AND, OR, and a NOT with nothing but NAND gates. Okay? Because it already has an AND gate and an inverter. Okay? And so what we're going to do indeed is we're going to use Demorgan's theorem to prove the universality. Because I've already showed you a little bit that we can use ANDs, ORs, and NOTs to build anything, and we're going to continue to. But we're going to prove that we can build an AND or a NOT using nothing but NAND gates, and that makes it so that we can build any circuit with just one type of gate. Okay. Now we won't do that unless we get really. We won't do that on a large scale unless we really have to get down into it, right? But this is going to help us with our simplification. It's going to help us with a whole lot of like seeing those like combinations and those patterns that are going to make us good at like solving problems and creating things. So what we're going to do is we're going to do universality of NAND gate um, through deed. Okay. so we're going to do a new circuit. All right. So up here, right beside the AND gate, we've got AND gate. All right. It doesn't show the little plop down, but we're going to take a 2-input NAND gate. Okay. Put it down here somewhere. Okay. What? All right. So we've got a 2-input NAND gate. Now, a NAND gate, let's talk about the logic of a NAND gate. Okay. We're going to go back and forth between my iPad and NAND gate. All right. So we've got a NAND gate here. Okay. And it's got 2 inputs. We're going to say A and B. We've got an output Y. All right. Now, an AND gate, go down here, and we're going to do an AND gate. All right. So A, B, Y. So 0, 0, 0, 1, 1, 0, 1, 1. And then an AND gate, only true when all of them are true. All right, so a NAND gate is going to invert that output. Okay, so it's like putting an inverter at the end of all of our output. So that 0 will become a 1, so forth, so forth. All right, so NAND right here. I'm going to look at NAND. Okay, let's look at ORs because we said that we could use an OR, or we could use a NAND gate to make an OR. So we need to make sure that we know what we're talking about. And we'll do a NOT right here. All right. So we've got those things. So, all right. Now we need to figure out how to make a NAND gate into these other things. Okay. So with the Demorgans, we showed that if you invert the output of a gate, you get the opposite gate with its inverted inputs. So if we invert an AND gate, that means we get the opposite gate, an OR gate, with all of its inputs inverted. Okay. So a NAND gate should be the same thing as an OR gate with all of its inputs inverted. Let's prove that real quick. Okay. All right. So if we have a 0, 0, means we got a 1, 1, we get a 1. That checks out. If we get 0, 1, we get a 1 right here. That's going to check out. Basically, if we've got a 0 on any of these inputs, we're going to get a 1 on an input of an OR gate, and we're going to get a 1 out. The only time this is going to be 0 is if both of these are 1, because then both of these would be 0. Follow? Because the 1 would invert into a 0, and the other one would invert into a 0. So the only time the OR gate is false right there is if both of those original inputs are true. And look, that does hold true. Like the NAND gate is an AND gate with the inverter at its output, and it's going to be equal to the opposite gate with its inputs inverted. Okay? All right, so how would we get just a regular OR gate, right? So if we use a NAND gate, that's just like having an OR gate with its inverted input. Now, I don't want to draw an inverter every time, okay? So I'm just going to use the circles from this point forward, okay? So that's an inverted input OR gate. Well, how can we invert, or how can we uninvert? Well, if you reverse, you're back to the original, right? So if we put a knot here and a knot here, okay? If we have a 0 here, that'd make it a 1 here, which would make it a 0 here. So now with those extra inverters, we're able to get the real inputs into the OR gate now, right? So if there was a way to put knots in front of that OR gate with the inversion, then we got a regular OR gate. Okay. Well, I said that we should be able to do everything with the NAND gate. So I showed you how to get to an OR with some inverted inputs, and if we could get that NAND gate to start working on those knots, we might be okay. Well, what about this? Look at when the NAND gate is both 0, the output is 1. If the both inputs are 1, the output is 0. Could we use that to our advantage? Well, yeah. What if we tied both inputs of that NAND gate together? So now we get a 0, and that's going to be 0, 0 on both ends, and that's going to give us a 1 out. If we put a 0, or if we put a 1 in there, that means we get a 1 on both inputs, and the NAND gate's going to give us a 0. So if we tie both inputs of a NAND gate together, we're going to get an inverter. Okay? So if we took a NAND gate and then we took another NAND gate and tied its inputs together. Sorry. Erase some of this. Okay. We took a NAND gate and we tied sometimes it's hard for me to draw. Sorry. We tied both of the inputs of that NAND gate together. Right there. We're going to get an OR gate. Okay. These are NOT gates. All right, so this whole thing is an OR. This whole thing is a NOT. What about an AND gate? We said we need an AND gate, right? So we've got an AND gate, which is the inversion of an AND gate, right? Well, what if we want to invert that inversion? We put another NOT there, right? Well, we're only using NAND gate, but we can make a NOT by tying both ends. It's hard, man. It's hard doing that. tie both inputs that not or that NAND together, and this is going to give us our AND. Okay. All right. So what we're going to do with deeds is we're going to make an OR gate and an AND, or an OR gate, an AND gate, and a NOT. Cool. All right. So let's make a NOT. Okay. So we're going to call this NOT, or an inverter. We're going to hook up that to that, that to that. Then we're going to tie an input switch to here. And we're going to prove that that is an inverter. Okay. When it asks you to save it as Demorgan. Okay. I'm going to give y'all a whole extra 100 for these simple little things I'm watching this video. Okay. So name this Demorgan. When we play it, we've got an inverter right here. This was the thing that I had that aha moment, and it changed my life. Like, it took me a week to get Demorgans. This was the exact subject that made me devote my life to this, because as soon as I sat down, and I took that time, like, it was harder for me because I was just going out of the book. But I couldn't understand, what they were talking about or how that applied to anything. But once it dawned on me how it worked, it opened up a whole lot of other stuff, and it gave me confidence for other things. So this was probably my most important lesson that I ever had. Like, not like, oh, well, shake a hand standing up or anything. It's this right here was the start of me finding my passion. Okay, so if it takes you a week, or if it takes you two, let it take you that time. All right. But whenever I had the aha moment with this, that's when things started going good for me. All right, so now we've got a NOT. We want to take another NAND gate, and we're going to make an AND gate with it. All right, so we're going to prove it this way. We're going to take that NAND, and we're going to tie you can do Control Y to I think it's Control Y to get wire to come back. We'll find out. All right, on this output, we're going to call this an AND gate. Okay. Now we're just using NANDs to do this. So Control W. It was Control W. All right. Now we need two inputs. We're going to have A. We're going to have B. Control W. All right. Now, before we go, let's save Demorgans. All right. An AND gate is only true if all inputs are true. We've got an AND gate here. All right. Trust me when I say, if you have an AND or a NOT, you have everything. And now I'm about to prove that you can have everything, all of those ANDs, ORs, and NOT, with a simple NAND gate. Okay? So we're going to take another 2-input NAND, and we want to make an OR. All right, so we said that like an AND gate or the a complemented output is the same as the opposite gate with complemented input. So if you have an inverter on the output, then you could flip that gate so an AND becomes an or an or becomes an and it's the same thing as if those inputs were inverted. So what we need to do now is we need to uninvert those inputs. Like a NAND gate is just like an OR with inverted inputs. We don't want inverted inputs, so we're going to have to invert those inverted inputs to get them back to regular input. So we can make inverters by tying NAND gates together, their inputs together. We're going to call this an OR gate. I'm going to do an A, B, we'll go and tie those together. Now, an OR gate is true if any of the inputs are true. So we're going to run this. We're going to say yes, save the current file to Demorgan. If any of these inputs are true, or both of them true, we're going to have a 1 there. All right, so we just proved the universality of NANDs. Now, NORs work the same way. There's a couple of things, like a NOR takes a couple, like an extra transistor or so to build than a NAND gate. So we use NAND gates. Like they're saying, I mean, like if you can do anything over and over again, you get good at it and it gets cheap. So instead of having, a bunch of different gates, we can use NAND gates and make all of the circuit that we want. Now, this helps us when we need to make things simpler or we need to compile it into like a FPGA, like a field gate array, to make like a GPU or something. Or, like a number crunching, supercomputer type thing, or, a Bitcoin miner or something. We're using NAND technology because instead of doing like it all in software, we can do this math almost at the speed of light, because that's how fast electrons are running, and like propagation delay through these are next to nothing. So we can do really fast, complex parallel calculations using logic gates, and we've gotten really good at making NAND. Now, we might not use NANDs all that much unless we get into a tight, okay? Like, they help us get out of tights, and they help us keep things cheap when we're going to put it on a wafer, like on, like a piece of silicon to actually make a lot of things out of. But when we're trying to learn how to create, we're not really getting down to the nitty gritty of, okay, well, I can only afford a couple thousand of these. Like, we're learning for learning's sake, okay? And you can spend a good year by itself in optimizing things. That's not what we're here for. We are to get it to its simplest, but when you're talking about like speed and like density and all the big things that you'll be worried about if you are trying to make a custom gate array, we're not going there. All right, so universality of NAND gates, we'll use some, but it's not like we're going to get everything built off of nothing but NAND, okay? Because it's a little bit more convoluted to do this, like, than to do an AND gate, right? Okay. So I appreciate y'all. All that you have to do for this 100 is to, uh, like, I would turn in a screenshot, like, have it running and then do like a snipping tool or whatever. You can Google how to do a screenshot and send this in. Like, it's going to be a lot easier than sending in a bunch of deeds files, and that's how we're going to start doing it. So, you can use the snipping tool in Windows, or well, you have to have Windows to be doing deeds anyway. So, send a screenshot of you haven't done this, and you're gonna get 100. All right, I appreciate y'all, jokers. Have a great one.